Great. Thanks, Osni. So hello, everyone, and welcome to the Variorum Lecture Series. Just as a quick reminder, we will be or are recording this Zoom session in case you want to refer back to it at a later time, or if colleagues that couldn't join us want to watch this presentation later. We will be posting this web recording following this tutorial, as well as the slides. And if you would like to follow along on your own while we're giving this presentation, we did post a copy of these slides at the link that's there at the bottom on Read the Docs under the presentation section. This is the second of our 2 modules in our series. We will be repeating both modules again starting next week in case there's been a time conflict or a preference for a different time. Those will be at 4:30-ish Pacific time next week. Today, we will be presenting Vari-Arm integrations with different system software and tools. The presenters today are from Lawrence Livermore National Laboratory. My name is Stephanie Brink, and I am joined by my colleagues Tapazia Patke, Anaruta Marate, and Barry Roundtree, who will be presenting various topics throughout this tutorial. If you have any questions while we're presenting, feel free to write them in the chat, or you can come off mute and interrupt us, and we can get your questions answered as we move forward. So here's the agenda for today's module. We'll spend the first 10 to 15 minutes or so recapping the HPC Powerstack Initiative and the Variorm library that we discussed in Module 1. The next 3 agenda items will dive into how we've integrated Variorm into various components of the Powerstack. So we'll look into how we integrated Variorm into a job level power management runtime system known as GOPM. We'll discuss integrations into 2 different system level power management infrastructures, Slurm and Flux. And finally, we'll discuss application and workflow integrations with Cocos and Caliper. We'll end today's module by looking at some of the upcoming features that we have planned for Variorum. And of course, we'll have time at the end for questions and discussion as well. So with that, let's get started. I see something in the chat. Is that something I need to review?
No, keep going, just a link.
Thank you. Perfect. Thanks, Osni. Okay, so there are many different ways to manage the power of a large supercomputer. At the highest level here on the left, you have the facility in which the supercomputer sits, and that may be enforcing a cluster level power bound due to maybe the peak power pricing from the electricity provider company, or possibly wanting to be more energy efficient overall. The constraints and the requirements at the site level will be driving the requirements of the subsequent levels in this figure, all the way down to the rightmost level, which is where you have your component level constraints, knobs and controls. The site level constraints are used by a power aware resource manager or job scheduler on the supercomputer. And this will be taking in those site level or cluster level constraints and setting a power bound at the job level. Within your jobs, you might have different levels of load imbalance, and you may want to allocate more power to a particular task to speed it up while removing power from another task in order to correct the imbalance. We can see this imbalance, of course, in a variety of different applications, in big workflows, as well as in application and performance tuning in order to improve the performance of the critical path of your application. Furthest to the right in this figure, we have the monitoring and the control knobs of the different components within the node. So this could be your GPU, your CPU, your DRAM, and other components that are contained within our node these days. There's also this notion here with this database here of having application profiles, and this might or will contain historical information about the application and how it performed, and we can use this information to improve our job scheduling and application level tuning and make them a bit more intelligent than doing this algorithm without the application profiles. So this figure was originally put together as part of the HPC Powerstack Initiative, as we talked about in Module 1. And this group, an initiative, aims at standardizing how to do power management at a full stack level and across the different levels, as well as understanding the interactions between and across the different levels in this stack. For more information about the Powerstack Initiative, if you'd like to be involved, we have posted the link down here at the bottom of the slides at github.io. So the Powerstack Initiative includes several different collaborators from all across the world. We have collaborators across the US, Europe, and Asia. It includes collaborators from industry, the research labs, as well as academia. Within this community, we have developed 3 different working groups at the 3 different layers that we talked about at the previous slide. So we have a working group focusing on the component level knobs and controls. We have a working group focused at the job level, and then a working group focused at the application level. One of the Powerstack prototypes was developed under ECP a while back and uses Slurm, Variorum /MSR safe, and a job level runtime system known as Gopm. And we'll be going into more detail, of course, in the next few slides on this integration. Another prototype that we'll be covering that was also developed as part of the Powerstack Initiative includes Flux and Vari-Arm, and this is also going to be discussed. So recapping what the Vari-Arm library is, Vari-Arm is a vendor-neutral user space library for power management. It provides platform-agnostic, easy-to-use, front-facing APIs for you to integrate into your applications. Vari-Arm is an evolution of a Livermore library known as libmsr. So all the original functionality that we had for libmsr, which targeted Intel platforms, has been brought over into Vari-Arm to support Intel platforms in Vari-Arm. We have designed Vari-Arm to target several different architectures and platforms, as well as their individual features with a common API. And under the hood, Vari-Arm is going through the different mechanisms in order to support the different knobs and controls. So with Intel, we have, actually with Intel and AMD, we've got the RAPL interface or the ESMI for AMD specifically. For IBM, we have the Opal layer. For NVIDIA, we go through the NVML library. For ARM, we use HWMon. And this box here is for a combination of the two. There's this power shifting ratio that is provided through the Opal interface as well. Vari-Arm is a C-based library, and we use function pointers as part of the build to set the particular implementation of the feature for the target architecture. And because of the way that we've designed Vari-Arm with this new Json interface, we're able to integrate Vari-Arm into other layers of the power management stack and are able to pass information that Vari-Arm knows about up to the other actors so that they can use that information to make decisions. This bottom right figure here is showing a high-level overview of the system architecture for Vari-Arm. So highlighted here in this red box is where Vari-Arm sits. And you can kind of get a sense of what the high-level interfaces look like that Vari-Arm currently provides. You can obviously look in this header here for a bigger set of the different functionality that's provided. Underneath the high-level interfaces, as I mentioned, the calls will go through the different kernel interfaces that are provided by the different platforms, whether that be MSR Safe, Opal, NVML, or HWMon. And then we're obviously targeting different architectures. So here in blue are the current 5 supported architectures in Varior. Our AMD CPU port is currently under review and is up for a PR, so that's not quite merged in yet. And then you can see in gray the different architectures that we plan to support in Varior down the line. So Varior is open source and up on GitHub at this link here on the bottom right. We have provided read the docs web pages for specifics, information on how to access the underlying knobs and controls on the different architectures that we support. If you're interested in knowing how things work at that level, we also provide information on how to build Vari-Arm, as well as if you're interested in writing your own port and extending to a new architecture, we also have docs on how to do that as well. Our current release is 0.4.1. This was released back in April of this year. This extended our support to include NVIDIA and ARM, as well as you'll see the AMD port that's under review. And this current release also extended Variorum to include a Json API. And again, this was to allow us to integrate with external tools like Caliper, Cocos, and Gopm. So one of the things that you might have noticed from the system architecture figure is that many of Variorum's APIs are for printing information out to standard out, or in some way that the user can parse and make nice figures on what the power usage is or what the energy consumption is. And so while this was a nice interface to understand the hardware level metrics and kind of get a sense of how tuning different knobs impact those metrics, this really limited Variorum's ability to send these metrics along to another tool. So recently we've added this JSON interface that's vendor neutral. And this API here, this Variorum get node power JSON, is one of our first APIs that uses this JSON interface that our tools can integrate into their codes. So currently we've defined a set of objects and keys that right now we're specific to IBM, since that was where we were targeting, but we're still working on this JSON interface to extend it to the other architectures that we have, like Intel and NVIDIA. And so we'll be defining these objects and keys to encompass all of those architectures and the specific features that they support. And just to give you a sense of what we've done here with this, we've been able to report end-to-end power usage for Cocos loops by using this JSON interface. And another thing that we've done was been able to provide power information to the Flux scheduling model, so that as Flux is scheduling its resources, it can have a sense of how much power is available at that moment in time. And with that, I think I'm transitioning over to Aniruddha. So I'll stop sharing.
All right. Let me try to share. Oh,
yeah, no, let me stop sharing real quick. Nope. Stop. Got it.
All right. PowerPoint. Are my slides visible now?
Yes.
Okay, awesome. So yeah, so thanks Agni for the introduction and recap of the concepts on Variorum. In this part, which is going to be a chunk of this, module 2 of the tutorial, I will be focusing on how we interface different components of Powerstack with Variorum at the center, and through it with the hardware. And also, I'm not able to see the chat, so if please feel free to stop me if there is any question.
Aniruddha, I'm monitoring it, so go
Great.
ahead. I'll interrupt in case someone has a question.
Awesome. Yeah, great. So first I'll focus on the vendor neutral interfacing of third-party runtime systems with the underlying platform using Variorum. In this case, the primary focus will be on Gopm and NRM. We'll also talk about Conductor, which is a research-based runtime system that we productized using Gopm, and we'll touch base on Cocos a little bit. So this work is being conducted by multi-organization collaboration, including our colleagues from Intel, Argonne, National Lab, IBM, NVIDIA. I forgot to put ARM and AMD as well. So I wanted to mention that before we begin. So the agenda for this part will be threefold. In part one, I will give a high-level overview of GOPM runtime system. The second part will cover the agent and platform IO extensions of GOPM. I will then cover a demonstration of usage of GOPM. In part three, I will cover our contributions as part of the ECP Argo project towards incorporating a functional Powerstack prototype. This will include a plugin for GOPM called Variorum IO. It will also have integration with alternate implementations of runtime paradigms, in this case NRM, and also a custom GOPM algorithm called Conductor Agent. So this slide is to give you a high-level context or framework for the power stack based on what Stephanie presented earlier. This figure shows the traditional power management software stack. The site level power or energy goals are at the top are translated into cluster level goals, typically handled by scheduler or resource manager. They are then translated into job level targets that are enforced by the job level runtime. And then that gets translated into node level controls for power management, as we talked previously. So in this part, I will focus on specifically the runtime system approaches for power management. These approaches um, either are static or dynamic, which manage the job level power statically or dynamically to improve application performance or address a site specific goal. Examples of such runtime systems include IntelliGOPM, Conductor, Power Aware, Cocos, and so on. So at the runtime system level, here's the high-level problem.
I'm going to interrupt you for just 1 second. I wanted to mention that GOPM is a broader effort. It's developed by Intel. Like it's an open source framework developed by Intel. And
yes, I have that.
You have that, right? Okay.
Yes, I mean, I wanted to give the high-level definition first, right? What we're playing under, right? So,
I wasn't sure if you were covering that because I put that note in the chat. So you have it. So I will stop. Go ahead.
Okay. Yeah. So I mean, so the high-level question is, given a job level power constraint and a number of nodes, how to optimize application performance. So that's where GOPM comes into picture. GOPM is a power and energy aware runtime system for large scale HPC systems. It's an open source, production grade, scalable, job level, extensible runtime framework. It provides extensibility in different ways. It addresses some of the limitations of previous work, which is typically research based. So research based codes are ad hoc and they only address specific needs for a site and a situation. They target specific system or memory model. They have scalability issues. For example, Conductor has scalability issues, and they rely on empirical data, which is not always practically useful. Also, this the development of GOPM is funded through Argonne National Lab contract and has active collaborations with several sites, including Lawrence Livermore. So here is a high-level system model for GOPM. At the left-hand side, the site administrator provides a power constraint to the power aware scheduler. When the user launches a job, the scheduler applies a static power limit to the device and hands over the power management responsibility to GOPM. GOPM has two main components at the center. The job tuning component runs the user level application while transparently tuning power controls on the system. So in theory, these could be any type of existing APIs to the system, including Variorum or Power API. The job monitor generates a per node trace file and also a job level report. These are some of the capabilities of GOPM. I'll just quickly go over them. It enables a transparent analysis and tuning of application. It performs feedback-guided optimization. It takes the power assignment decisions based on the application behavior at runtime if you enable the right plugin. It uses tunable control knobs in the response to that behavior. It supports built-in optimization algorithms for different aspects of a runtime system. For example, static power capping. They have energy reduction agent or algorithm. They have a load balancing algorithm through power balancing, and there's also some effort towards lowering the synchronization costs. These are the high-level components of GOPM. First is the GOPM core infrastructure at the center this abstracts out common runtime functionality. The second is the application markup API on the right for extended insights into application behavior. The third is the extensible agent and platform IO interfaces, which we'll talk about later. The agent interface provides a way to abstract out the core tuning algorithm that you want to develop. And the platform IO extension abstracts out the interaction with the platform. And the fourth one is the endpoint interface that is used to interface with higher level entities such as scheduler or administrator. I won't be focusing on endpoint in this tutorial. So let's do a quick overview of GOPM core, which provides the hierarchical communication and pluggable interface, pluggable infrastructure. So at the heart of GOPM infrastructure is the hierarchical control and telemetry transmission. This is a logical view of GOPM infrastructure. So at the top is the root controller. There's only one node in the job that is root. The root is connected to the intermediate levels using an MPI communication overlay. So GOPM piggybacks on the application communication overlay when it runs along with the application. At the bottom is the hardware layer that communicates with the hardware. Note that each node has a leaf controller, and some nodes may have aggregators. And so this is a logical structure that fits on or maps on the physical structure of the MPI tasks. One core on each node is dedicated to the GOPM process. If you run GOPM in process mode, or one GOPM thread if it runs as part of one of the MPI ranks. Rest are assigned to the application. Each leaf controller also communicates with the platform for control and telemetry. So you can extend the controller side functionality using the agent plugin interface, and you can extend the platform side functionality using the platform IO interface. So GOPM is available on GitHub at the link that I provided. GOPM provides a wiki as well where you can track activities, documentation, and other things. The build process uses a standard configure and make workflow, and it should build out of the box on most systems. I won't be able to give the demo of GOPM build, so I'll skip that. And these are the input and output files generated by GOPM when it runs alongside the application. The policy JSON, so we'll look at the input first. So policy JSON is submitted by the user or the administrator. Typically, it has a power budget and the algorithm that you want to run along with for the power budget. The application generates and populates the profile, and finally the agent generates the traces, and in this case, one trace per node, and as I said, one report per job. So I want to show a demo like a step-by-step demo of how we can use GOPM. I guess if I try to share, okay, that didn't work. Okay, so let me share the demo separately. Okay, is the demo, is my screen visible here?
Yes.
I guess, okay. Okay, so first I'm going to show the environment in which I am using GOPM. So understand that GOPM is already built. This is on one of our Lawrence Livermore's clusters called quads. As you can see, we have Intel compiler, MVAPH, and MKL loaded. So when we compile an application and the GOPM is already built, it is built with those components. I'm showing GOPM components like the launcher, especially the launcher, already installed in install ECP, and in the lib folder I have the libgopm.so, which gets linked with the application. So next, yeah, and this is the include file that you have to include with the application. So that is how the system is set up. GOPM comes with a tutorial directory with a bunch of tutorials. I'm just going over tutorial 0.c. This is a simple MPI application that initializes and finalizes, doesn't do much, and sleeps in between. Right. So what we want to see is how to, I guess, compile this this application with GOPM, and what happens when you run it, and what kind of output is generated. So I'm just going to fast forward a little bit. So I'm specifying tutorial 0.c and a bunch of flags. So I compiled tutorial.c. Now I'm linking it with libgopm. So get tutorial 0 binary. Now the second step is to generate the policy JSON that we want to run this application with, right? So you don't really have to create an application, GOPM JSON from scratch. You can use the GOPM agent command. Again, this is from GOPM version 1.1. What we are showing is there's an empty policy JSON because we specified the monitor agent. Monitor agent only collects telemetry and doesn't do any power assignment. So this is the simplest GOPM run. I also ran. I also got a couple of nodes on quads, and so now I'm launching tutorial 0 with srun. Prefixing the entire command with GOPM launch. So GOPM launch does a bunch of things, including process or thread affinity, clean initialization, and some bookkeeping. So it's always useful to use this launcher instead of trying to launch it ourselves. I'm launching 8 MPI ranks on 2 nodes. I'm running GOPM in the process mode. And I specified what the report file name should look like and the trace file name should look like. Notice the double dash before tutorial, so that's how GOPM launcher knows how to separate the runtime options with from the application. This will run, I guess, for 5 seconds and stop. So now we'll take a look at the files that were generated. So you can see there's a tutorial 0 report that was generated. So if you open it, you will see node specific information in that one report. It will show how much time was spent in different regions. In this case, there's only one region as highlighted, and the application took five seconds. This particular report is not very useful or interesting. As we start to apply power caps, you will see a lot more interesting stuff. There's still things like DRAM energy, package energy, and so on, which might be useful. What's more useful is, or are the traces that are generated per node. So let's look at the traces generated per node. I'm not I have to speed up here. Okay, so now I'm opening the trace generated for quartz 43. There's some preamble which is commented out just to give you a log of what happened. The first entry in each trace file is a header separated by pipe, so you can post process it in whichever processing tool you use. There's a bunch of things going on here. So GOPM records time, region ID. um, Progress is not useful in this example. What's useful is the energy package, energy DRAM, power package, power DRAM, and uh, these are fine-grained samples. So if you have a long-running application, you get a long trace. So yeah, so that's how you can run. I mean, tutorial 0. I have another example that explores uh, you know more nuanced example from the tutorials directly from GOPM. If you have time, I'll get back to that. I'll show that at the end of this section. So let me stop. I guess we have to stop sharing again. Okay.
Hey, Honored. I
Yeah.
think, do you hear your fan spinning up?
Oh, yes, I do.
So
Yeah.
today I'm hearing it. I don't know
Okay.
if it's I know you're still showing some videos, but
Oh, it might be because of the video. Actually, yeah, it should be because of that. Hopefully it will subside, but if not,
yeah,
I
it didn't pick
apologize.
up. Yeah, it didn't pick
Okay.
up till the video was playing.
Okay. Okay. Uh, yeah, let me. I'm not sure what to kill here, which is our go-to solution. But okay, I can see some activity subsiding on my system, so hopefully the fan will too.
Mhm.
Um, okay. Okay. Let me share again. Okay. So yeah, so that was GOPM configuration, build and launch of application. These slides just provide additional steps to give you a reference for for what it takes to build an application with GOPM. I'm just going to skip over those. There's some additional, so in step 4 here, there's some additional information on what other options can be used. So especially GOPM agent, policy report, and so on. And there's an example of how to do that. So yeah, so this is just for reference. So this is the example I was talking about. If I have time at the end of this section, I will show this example. Okay, so that was GOPM core and how to build an application with it. The second part of GOPM is the application markup API. We can use this markup API to incorporate the knowledge, of or knowledge about the application behavior into the power management decisions of GOPM. So GOPM is better equipped about what the application is doing, and what it can do about it. Uh, I'm not going to go in too much detail of the Markup API, but here is a high-level overview. Um, there are 3 types of Markup APIs that GOPM provides. One is the application region markups to outline interesting regions in the application that you want to handle. You want GOPM to handle differently. Second is the epoch, which might have changed since but so essentially. It indicates the end of time step. And third is the OpenMP region specific markups that are similar to the first set of APIs. So yeah, I think that overview is sufficient. If you are interested in looking at how this markup is used, GOPM documentation is a good place to start. So the second part um, is about how we can extend GOPM to add functionality and platform support, right? So this is extending GOPM's algorithm and its applicability to different platforms. This will provide the basis for the Powerstack deployment I'll talk about later. So GOPM provides extensibility through its agent and platform plugin interfaces. The agent interface provides ways to extend the power management, profiling, and accounting of the job. And the platform IO interface provides access to low-level uh, uh, telemetry and control like MSRs, as well as application context. So GOPM comes with two important power assignment agents, among others. One is governor for static assignment. The other is balancer for optimizing job level power assignment while extracting maximum performance. In our extensions, we leverage the balancer agent of GOPM to include application configuration or concurrency, as I'll explain next. Similarly, on the platform end, we introduced Variorum IO as a plugin to interface GOPM with Variorum. There are more examples of both of these types included in the GOPM source. This also includes an example agent, which is a simple framework where you can start building such agents and platform IO examples. So first I will talk about the Conductor agent plugin that we introduced as part of the Powerstack. For a quick background, a naive solution, which will be our reference baseline, is called static power allocation. In this solution, the job level power is equally distributed and enforced over all nodes. A static setup that uses this solution typically uses processor level power capping features, for example, Intel RAPL. For that application, a configuration is selected that operates under the assigned power limit. This configuration includes things like number of cores to run and frequency, or in this case, power limit through RAPL. So users typically select the maximum number of cores when they run an application. This is called the packed configuration, and the frequency and power limit, or frequency or power limit, depending on what is available, is set based on how much power the application consumes at the maximum thread count. So this naive task or thread configuration may be inefficient. So here is how that typically leads to inefficient configuration. Here is an input configuration that is defined in terms of number of cores and frequency or power limit, and the output is the execution time and power usage. So power usage is on the x-axis. So this is a scatter plot of execution time versus power usage. Different symbols show different thread counts. So we collected exhaustive data for a computation region of application called CoMD. So each data point shows one run of that computation region. So as you can see, the packed configuration with 8 threads, as shown in black symbols, is always inefficient. That is away from the origin, and so inefficient in power and performance compared to the best case here, which is the five thread configuration that is shown in red. So if you have a power constraint that is a constraint on the x-axis, you will see that so in this case the power constraint is around 70 watts. So you will see that the packed configuration is up to 30% slower than the best configuration, which we know exhaustively, of course. So without a runtime system, finding the best configuration requires exhaustive search. which is prohibited. The second issue is there may be a portion of the assigned power that's left unused by a lot of tasks. This is especially true for a load imbalanced application like Paradis, for example. So Paradis has some tasks that consume a lot of power, and other tasks are idling that are not on the critical path and consume lower power. So we can leverage, or we can optimize that situation, as I will explain later. So to address these drawbacks, we developed Conductor. Conductor was, again, this is a high-level overview of what Conductor is. Next, I will talk about how we prioritized it. Conductor was designed with two goals in mind. One is to speed up computation on the critical path and reduce application execution time. And the second one was to use a power-efficient configuration to speed up that critical path. To realize these goals, we needed to dynamically identify two aspects of application. First was computation region that is on the critical path versus computation that is off critical path. And the second was power and performance profiles of each computation for each task. So here is the conductor algorithm. The first step of this algorithm is the configuration exploration step. So conductor assumes that applications have time steps. So the idea is to explore sufficient configurations for each computation region. So a few number of time steps. Here is an example of a time step. So we have k sub 1 to k sub n unique configurations. And at the end of each time step, and altogether distributes power and execution time for each time step to all tasks. So it monitors that and then sends out that information. Note that the slowest configuration contributes to the overhead caused by this step, right? So in this case, k sub n is shown to be the slowest one. So here's a sample scatter plot of that data, right? That's disseminated at the altogether for one computation region for all configurations. So for all configurations on the blue curve are Pareto efficient configurations, which means that all configurations outside or above that curve are power inefficient. So for example, a power constraint of 40 watts, this configuration as shown here, 70 watts is most efficient. So k sub opt essentially is that configuration. So conductor first finds out that configuration. The second step is the power reallocation step. So I just advanced the flowchart a few steps. In this part, conductor checks if a computation is non-critical. If it is non-critical, it slows the computation down by reducing its power and then uses that excess power to speed up the critical computation in that time step. So the way conductor assigns this power is by selecting another power efficient configuration at that higher power usage that was explored earlier in the previous step. And on the right is, the histogram shows the impact of or before and after impact of the power allocation step on Paradis application. So the plot at the top is a histogram of average power usage of Paradis tasks. A lot of the tasks are centered around 65 watts here, as shown by the circle. With the power reallocation step, some of these tasks move to 62 watt range, and the unused power from those tasks is allocated to the critical tasks, which causes some tasks to run between 70 watts and 75 watts or around that point. So with that, the total job level power constraint is still met, but the overall application execution time is reduced. So now, so this is the background on conductor. So to implement that in or with GOPM, you basically leverage the power balancer agent of GOPM, which is not configuration aware or concurrency aware. It has so our contribution has 4 components. First is the OMPT class for thread configuration, exploration, and selecting power efficient configuration during regular execution. GOPM provides readily provides a way to um, piggyback on the OpenMP profiling that is enabled if you compile it with the right options. The profile class is used to report end of time step to enable configuration sweep. The config app class is used to do application profiling and generate the Pareto optimal configurations as I showed before. And the config agent class is used to share the telemetry that is collected to the power balancer, part of the code. So we are essentially using that code and feeding it with additional control knob, which is concurrency. So here is the end result for 2 applications, again, CoMD and CoMD imbalance. CoMD imbalance is just an load imbalanced version of CoMD, which is pretty regular. The 2 bar plots compare static uniform power allocation with 2 runtime solutions, GOPM and conductor agent. The y-axis is execution time, so lower is better. X-axis is power budget. So the blue bars correspond to legacy GOPM, and red bars show improvement with conductor agent. And you can see that with conductor agent, there is consistent performance improvement across different power budgets. So if you want to check out these contributions, the code is available in the following links eventually. So currently we are working to refresh the conductor agent plugin code to merge with the latest GOPM code base. And we also plan to integrate or work with the JSON interface contributions that have been made recently to Variorum. So that's our plan moving forward. So with that, the third contribution is the platform IO plugin for Variorum. So I'm not going to go in depth here. The motivation essentially is to use GOPM in a platform agnostic fashion, or vendor neutral fashion. So for this, we primarily targeted static power allocation first as the baseline for prototype. The components include a platform IO plugin called Variorum IO that maps GOPM specific data structures to Variorum's APIs. And on the Variorum end, the contributions provide a low-level API or APIs to aggregate low-level signals and pass them to GOPM. This has been only tested so far on Intel platform, but we are working on mapping other like the interfaces from other platforms so that this we can run GOPM in as vendor neutral manner as possible. The main challenge in that process is the translations that we need to perform in the Variorum IO plugin to translate platform specific controls and signals to what GOPM needs in a vendor neutral manner, and that's typically not straightforward. But Variorum makes it easier to implement Variorum IO implementation. In tandem, we have an ongoing work with the JSON API, as I mentioned, and so that will enable evaluation on different platforms as we move forward. And the code contributions and documentation for Variorum IO are available on these 2 links. So the third part of this, are there any questions or any comments? I'm not able to check chat. Okay, so the third part of this tutorial is about integrating NRM, which I'll talk about, GOPM and Variorum. So here's the background on NRM. It's a runtime system implementation from the Argonne National Lab team. Essentially, NRM is a daemon process running on the compute nodes to centralize the node management activities. These include job management, resource management, power management. So the figure on the right shows how NRM presents the view of the underlying platform to the application. Essentially, it uses slices for resource management. So physical resources are divided into separate partitions or slices. It helps in improving performance isolation between the components, and it's meant to be application transparent. So so when you run the application, it doesn't necessarily know that you are running in the slice. Um, so the node resource manager has two components, NRM daemon and NRM client. The NRM daemon manages it's the hardware facing layer. So it manages the power at the node level, works in a closed control loop. It obtains the power limit or goals that has been set by the higher level entity. And it acts on application workloads. So again, it uses application telemetry wherever it can. The NRM client launches with the application and manages the application during runtime. It relies on self-reporting by applications, and it identifies the application critical path if it is able to get the application profile. One thing to note is the way this setup is different instances of NRM on different nodes do not talk to each other, right? So there is a GRM or global resource manager that was envisioned. Our plan is to replace or have GOPM right above NRM in the hierarchy, right? So GOPM takes care of the job level power management decisions across nodes, and it lets the NRM take care of the node level power management decisions. This is especially useful as we are seeing increasingly heterogeneous nodes with several different compute nodes and power domains that need to be handled at the job level. So this is one way of decentralizing or compartmentalizing power optimization goals, and which was essentially the motivation behind the integration between NRM and GOPM. So with this compartmentalization, you can tune different goals at different levels. For example, you can improve critical path at the job level, or instructions per cycle or instructions per second, whereas at the node level you can break it down to instructions per second per watt, for example. Of course, that mapping and translation has to be done manually or at the design time, but it has to be done once. GOPM can indirectly also support containerization or containerized workflows through this method. Currently, GOPM cannot or does not support containers out of the box. The limitation here is GOPM still does the power assignment at the physical power domain boundaries. So that is one limitation that we are currently trying to figure out how to work around. So the initial prototype for NRM and GOPM integration involved writing a common launcher for GOPM and NRM. So when you launch the application with NRM, it runs GOPM along with the application. So GOPM is still part of the application process. It doesn't have a view of the entire node. But our testing has only so far covered single node experiments or exclusive node resource interface configurations. We haven't done testing of configurations where we have two or more jobs that are sharing the same resource. So that's something we want to tackle moving forward. Here is just for reference. Here is how you can build GOPM and NRM and then launch. So on the step 3, again, this is just provided for reference. We have introduced this launcher called GOPM NRM launch that essentially launches GOPM in that fashion. And that is provided, the code for that is provided again in the link that I provided earlier. So that covered the runtime integration part of it. Here is how in the next part of this tutorial, we will be focusing on the integration of resource manager or job scheduler with Vari-Arm, with an optional integration with the runtime system. So here are the different entities or actors, with each having different roles. So the user has the role of assigning power budget, running an application. On the right hand side, I've provided files or configuration specifications that the user is involved in designing. Slurm here is the the job scheduler that I'm looking at. It allocates resources and launches the job. Also, if it is power aware, it also derives job power budget. The Spank plugin here is part of the scheduler. It essentially provides a way to extend the functionality of Slurm. It's essentially we can provide two scripts or two methods. One that is run before the job is or the application is launched, and the other one is run after the application ends, but before the resources are freed. Plugstack.conf is where you can make that configuration. Then there is Gopm, and finally there is Varior. So with these actors in place, now I'm just going to give a high level overview of how we have stood up a prototype of a Powerstack integrating Slurm, Gopm, and Varior. So on the left hand side, we have a scenario where we have all these actors, and we have a scenario where the user does not specify a power budget, right? So the user launches an application. It may or may not be an MP application. So in this case, Slurm allocates resources, derives a power budget, and runs the Spank plugin on each node. The default power budget is used, which is derived from system level or cluster level power budget. That gets assigned at the start of the job using the Gopm's static power assignment method. More information on this method is on the GitHub link that I provided below. The idea is to have Variorum placed in between platform IO and the hardware, right? So we want to leverage the Variorum IO plugin in order to make this vendor neutral. So we don't have it yet, but this is the plan. Currently, we have something that works with Slurm and Gopm, and Slurm directly talks to Variorum instead of going through platform IO. The second scenario is where the user specifies a power budget, right? So again, at the start, Slurm allocates a node power budget that gets overridden with the user's power budget that the user specifies in the policy JSON object. Gopm picks up that assigned power, and depending on which agent you're running, either the governor or balancer, Gopm continues execution with the application while doing the power assignment. So, these two scenarios showed some of the use cases that we have dealt with. There are a whole lot of other use cases that I have not covered, but this is the high level like overview of what we have done so far. So yeah, so with that, I will hand it over to Tapasya, who will go over the Flux side of the Powerstack.
Thank you, Anirudh. I'm just transferring over to my slides before I share.
Yes.
Okay. And full screen mode. Is that visible to everyone?
No, it's a black screen on my side.
Yeah, same here.
Okay, stop share. Let's try again. How about now?
Yeah.
We see it. Yep.
Yeah, I think when I go full screen, it doesn't like it. So let's try that one more time. If it doesn't work, then I'll, not use the full screen mode.
Yeah, it doesn't like it.
Okay, all right. I'm hoping that people can see this now and it's readable. Try to make it a little bit bigger. Okay, so thank you, Anirudh, for covering GOPM and runtime systems and the integration with Slurm. So continuing on the same thought of, designing and deploying an end-to-end power stack, we saw one with Slurm and GOPM and MSR safe to be extended to Variorum just now. The second approach to this is to not have a runtime system as part of the power stack. So the previous one had three different components. It had a resource manager, which was Slurm. It had a runtime system, GOPM, and then it had the low-level knobs exposed through either MSR safe directly or through Variorum or other potential node level libraries. The approach that we are taking for El Capitan, which is our upcoming exascale supercomputer here at Florence Livermore, is going to be skipping the runtime system part of it. So we are going to go from the resource manager directly to the node level management tool, which is Variorum in this case. The expected resource manager on El Capitan is going to be Flux. Flux is being developed in-house, and it has a completely new scheduling model to meet exascale challenges. So the key difference between something like Slurm or LSF or our traditional resource managers and Flux is the idea of hierarchical or nested scheduling. So basically, Flux enables both user space scheduling and system level scheduling, as opposed to just system level scheduling. So users on Flux can allocate mini partitions of the supercomputer and run their own Flux instance or subscheduler within that instance. So here's a picture that kind of shows that. So if you are a Flux user and you have some resources allocated to you by a system scheduler, which is denoted by this orange box, you can then spin up your own Flux instance within it. And you can also hierarchically spin up more Flux instances within that Flux instance. So it's an approach that lets you be highly scalable as well as highly customized towards your partitions. So you may have a few nodes that need to be power aware. You may have a few other nodes that need high throughput computing based scheduling. You may have a few other nodes that need, say, IO aware scheduling. So you can have a set of allocated resources and multiple subschedulers nested arbitrarily deep to meet your requirements. Typically, the hierarchy will be around 2 to 4 level deep. That's what we are expecting in production. But the model in itself does not limit you to that depth. So that's a little bit of background on Flux. Another breakthrough approach that Flux is using is that of resource data models being utilizing graph-based approach as opposed to a simple node-centric approach. So traditional resource data models tend to be quite ineffective when we start to look at resources such as power or network or IO, which tend to be flow resources, or even other heterogeneous compute resources, including multiple GPUs or multiple FPGAs on a node. So traditionally, systems were designed to be much simpler. They were designed to have node-centric models. For example, the figure here on the right shows how Slurm handles this. So Slurm has an idea of each node being a bit represented by a bitmap, and if the node is allocated, it's basically 1. If it's unallocated, it's 0. So there is no idea here that lets you capture partial node allocation, right? So it's hard for you to do this at the core level or the GPU level or the burst buffer level to maintain these composite bitmaps. Also, it doesn't let you change these allocations for flow resources. For example, if you have something like power, it's not a 0-1 allocation. It's more of a half the amount of power is allocated to resource A or job A, 10% is allocated to job B. So those kind of things are much harder to do with a bitmap, a simple bitmap-based model. So because HPC has become much more complex, and adding in these new resource types like power or IO or network or heterogeneous compute nodes is complicated, Flux introduces a completely new model to handle resources. So it uses a graph-based resource data model to represent schedulable resources as well as their relationships. And of course, a graph here consists of a set of vertices and edges. So you can have containment hierarchies like the ones shown on the left, where you can mark that a rack belongs to a certain cluster, or a certain set of nodes belong to a certain rack, so on and so forth. You can have a network connectivity subsystem, which again can tell you which core switches are connected to which edge switches. We can build similar connectivity subsystems for power or IO or GPUs. And then the composability of graphs allows you to combine these multiple graphs into a single resource model. So you can now say that cluster A can connect to something like the core switch. So you know that all of them belong together. And because of this representation, you can now allocate resources partially, or you can also allocate resources in a more dynamic way, where you can be aware of, say, the IO or the network or the power subsystem in addition to a containment subsystem. So it allows you to compose different resources during the allocation process.
Quick question.
Yes, go ahead.
So could you please explain a bit more about allocating power-specific resources while creating this data model?
Sure. So how about we reserve that for the end, Sid, because I want to get through the presentation, and then we can talk more about it, because there are a lot of different ways. So I'm going to show 2 different ways in which we are going to use this in production, and then there might be other ways to do it using just the power example, right? So
thanks. Yep.
So let's reserve that question for the last 5-10 minutes. That's a great question. So yeah, like I mentioned, I'm going to show 2 different ways of how Flux is planned for production use, at least at Livermore. One of them is through variation-aware scheduling, and the other one is through combining Flux and Variorum as part of a power stack to allow for management and control of power resources on the cluster. So we'll talk about these 2, and then we can go back to discussing the graph subsystem for power as well, Sid. So that's a third approach. So let's begin with the first one, which is variation-aware scheduling. We saw some variation data previously in module 1. This is just some more of it, just for this particular example that I wanted to walk through during the Flux presentation. So here's a real-world example. We are looking at the Quartz cluster, which is Intel Broadwell nodes, about 2,500 nodes in this cluster, each node having 36 cores. 2 sockets, 36 cores. And we kind of turned down the socket level power bound way low, right? So we went down to 50 watts per socket of power cap. And then we started looking into what happens when we run applications. So what we are running here is a single node version of MG, which is the red dots. And then we are looking at the second application we are looking at is Lulesh, which is again single node version of Lulesh, which are the blue dots. The y-axis on both of those charts on the left is execution time in seconds. The x-axis is the node ID that we are running on. So we have the x-axis goes from 0 to 2,500, and it is sorted by node ID. So we have not sorted the data by execution time, but by just showing the distribution of what it looks like across the cluster. What we've noticed here is that there can be significant variation, at least at low power caps, which is something that we were showing in a different chart earlier. And in these particular examples, we saw that there is a 2.4x or almost a 2.5 times difference between the slowest and fastest node for MG, and about 1.9 times difference for Lulesh. And you can see the same data as part of a histogram on the chart on the right. So this is MG, this is Lulesh, and you can see that there is a significant variation and distribution over there of performance classes. So we started with this data because we kind of wanted to see how we can classify different nodes to be variation aware. So the idea that we were essentially looking at within Flux was to create bins of different performance classes, because ranking every single processor is not feasible from a point of view of accounting as well as application differences, right? So you have a few slow nodes, but depending on the application, some of those slow nodes cannot be necessarily ranked in the same way. So we decided to create bins of processors with similar performance instead. And techniques for this can be as simple as you want or as complex as you want. In this particular example, I'm going to show a very simple technique. It's still open research to determine how many classes should we create, which benchmarks do we use to create these bins, and which parameters do we tweak. So what we did was we chose 5 classes, so 5 different performance classes. We chose 2 benchmarks, Lulesh and MG, because one is compute bound, one is more memory bound. And we decided to just go with a single power cap just for this data set. Our goal was to mitigate application performance variation. And we were not looking, in this example, we are not looking at run-to-run variation. So run-to-run variation is when you're running the same application multiple times and you see different performance. Instead, what we are looking at is rank-to-rank variation, which is if you have an application spread across multiple nodes and it gets one fast node and one slow node, then there is, you're bound by the slowest node. So from a scheduler's perspective, if you could allocate from the same performance class, so you minimize the application spread across performance classes, then that's an ideal way of limiting or mitigating performance variation. So that's the idea that we are going with here. It's not letting me. Okay, there we go. So we used a very simple technique to determine node performance classes. Here, basically, we have 5 different performance classes here, and the frequency shows how many nodes fit into each performance class out of the 2,500-ish nodes on quads. The very simple technique that we used was we took the combined time. So we took the time taken by MG, time taken by Lulesh, divided that by the median, divided that number by 2 to get the combined time, and then essentially subtracted, normalized that and used that normalized value to create 5 performance classes. So anything that's in the top 10% is performance class 1. These are extremely high performing nodes, and anything that's in the bottom 40%, which is performance class 5, are our slow nodes or inefficient nodes. So we came up with this very simple distribution. Of course, there are much better ways of doing this classification. You can use more than 2 benchmarks to begin with. You can also, use machine learning or more advanced classification algorithms to come up with this list of performance classes. But that's a problem that's out of scope for this discussion. So once you have the performance classes, the scheduling problem becomes quite simple, right? So essentially, what you want to do is, as far as possible, don't let an application spread across multiple performance classes. So if you have an application that's requesting a certain set of nodes, try to allocate from the first performance class or the second performance class to begin with, and then move on to the other ones, right? So it's a very simple algorithm. Of course, if you have applications that's requesting the entire cluster, there is not much that you can do. But for a majority of the applications which are small or medium sized, the idea kind of works well, that you pick from the same performance class or an adjacent performance class to reduce the variation. So let's look at the impact that it had in terms of results. So y-axis here is number of jobs, so frequency, and x-axis is the difference in performance class. So essentially, we want the difference in performance class to be 0 as far as possible, right? So we want to allocate all the ranks or all the tasks in an application within the same performance class. It doesn't matter whether it's the highest performing class or the lowest performing class. As long as they're within the same performance class, they would have minimal variation. So the first two charts here show traditional scheduling. So highest ID first or lowest ID first just allocates based on node ID. So, whichever nodes are available, it walks down the queue of jobs and says, okay, these are the nodes that are available. I'm just going to allocate based on the highest node ID or the lowest node ID. So this is what we do traditionally in all of our current supercomputers. And then the variation aware algorithm, of course, tries to minimize the difference within the performance class. And as you can see, by the time we actually start evaluating this, many of our jobs end up in the performance class, end up with a difference of 0 within performance classes. So for over 80% of the jobs, we are able to mitigate the variation, or at least minimize the variation significantly. Also, if you notice, performance classes of difference in performance class of 3 or 4 is exceptionally bad, because that means that your application is spread across the fastest or the slowest node. So both are included in the allocation. And the variation of an algorithm kind of just avoids this compared to the first two algorithms. So this was a very good result for us. This is already available in production through the Flux framework. So I can point you to the link. I think there is a link up here. So if you go up here and you can look at the policies, there is a variation aware policy in there, which can be used in production to minimize performance variation. The second example with Flux that I wanted to talk about was mitigating power swings, and we saw this particular figure earlier in module 1, where we were talking about different power swings for about 200 kilowatts on one of our applications or one of our workflows on the Sierra supercomputer. We've seen similar things with other workflows and applications. We expect this to become worse at exascale because we'll just have more nodes and more power to play with. So our technique to mitigate this is to include Flux and Variorum to predict and detect these power swings in advance. So presently we are working on developing a Flux Power Manager. The link is down here. It's not yet production ready. It's still research code, but it is planned for FY22 to be production grade. And what we've done here is that the Power Manager essentially looks across the entire Flux instance and collects data from each of the nodes and continually monitors this data. So we are doing 1-second samples at this point and be able to process that data to see whether there has been enough of a delta between the previous sample and the correct sample to be able to predict any upcoming power swings. So this is still work in progress. Currently, we are at the phase where we are just learning to monitor these through Flux and Variorum. And this uses the Variorum Json interface to develop a Flux system instance that allows you to monitor and control power. And we are working on the algorithms to be able to predict what comprises of a power swing, like how many samples do we need to study to indicate a power swing versus, what is a normal change versus what is an abnormal change. So we are still working on that algorithm. The figure here just shows how we can monitor power data on the Lassen supercomputer, which is a mini version of the Sierra supercomputer. And we are looking at an application called Lenet, which is part of the LBAN framework. And as you can see, we are currently able to monitor things like the node level power, the GPU power, the CPU power, the memory power, and then there is the sum of the components, which is GPU plus CPU plus memory, because in some cases we won't have the ability to detect node power depending on the underlying architecture that we have. So we've been working on this, and it's coming across well. The last thing that I wanted to talk about here was power monitoring with Cocos and Caliper. So these ports are also underway. We have a production version for Cocos as part of Cocos tools, which basically allows us to hook into this profiling interface for Cocos, and that generates per rank output for power data for any Cocos application or Cocos workflow. We are developing a similar service for Caliper at this point, and it's on our radar to basically test these ports for scalability as well as other benchmarks outside of the simple ones that we've tested so far. So currently we've tested mini MD and more simple benchmarks with Cocos and Caliper, but we are working towards integrating them into larger workflows like E3SM. There's a link here for the Cocos Variorum connector if someone wants to play with it. And I think with that, I'm going to hand it over to Stephanie. I can keep progressing the slides, Stephanie. I'm just going to mute.
Okay, sounds good. Thanks, Tapasya. So very quickly, we just wanted to cover some of the next steps that we have planned for Variorum, at least for the next, at least till end of year, maybe even further, at least for our research efforts. So on the left-hand side is just some information about our upcoming development efforts. We had a release in April of this year, and we are aiming to do another, I think, minor release towards the end of 2021. We're hoping that we will add support for AMD CPUs. There's a PR that's work in progress and needs to be reviewed by us and tested by us, and so we're working through that. Additionally, we're longer term, not for this release, planning to add ports for Power API specification as well as for AMD GPUs. Some of the other pieces that we're focusing on in terms of development is adding this notion of a high-level API or an advanced API into Variorum. And the goal here is we've been asked to have some functionality or accessibility into some of the low-level, very specific features for different architectures. And so giving users the ability to interface with the low-level knobs and controls is what we're planning for the advanced API. Moving over to the research efforts, I know we want to leave some time at the end for questions. Tapasya, of course, talked about finishing up our Caliper service for Variorum. We're also working to integrate into bigger workflows. You saw some of the work that's with LBAN and Mumi. Another effort that we are working on is GPU characterization using an application or a benchmark known as MLPerf. So the idea is to apply a power cap to the different GPUs on our Lassen system and understand how they perform under different power caps. The last piece in our research effort is to extend our Slurm GOPM Variorum Powerstack that Anirudh had talked about earlier and extend that to use Json. So it is a vendor neutral power stack. Next slide, please. That should be our last slide. So we just want to thank everyone for attending our tutorial series this week and last week. So we could tell you about the Variorum library and the different integrations that we've done. I will leave you here with some links to submit issues or features requests up on GitHub. We have a low level or a low traffic mailing list for Variorum users that you can subscribe to. And if you have any questions, please do email us. We've got a mailing list for Variorum maintainers, and that's the 4 of us that are listed on the first slide. And with that, I think we will open it up for questions. And if people need to drop off, I know we're a minute from the top of the hour, feel free to do so. And thank you all.
Yes, thank you, Stephanie. So Sid, going back to your question, I'm going to pause and share something else so you have some starting point and resources on Flux. So let's do that.
Thanks, Tapasya. Also, it's perfectly fine if there are other questions on the call which are higher priority. Maybe we can take that from the audience.
Sure. So let me quickly address yours and then we can go on to other questions. So within the Flux framework, I don't know if you can see my browser right now.
I can.
Yeah, so if you go into Flux framework, Flux Sched, which is the scheduling component for Flux, there is a utilities folder for resource management. And in here, there is something known as resource query utility, which is our very simple test framework for trying out any new policies. And you can read about this more, like it gives you the ability to allocate jobs. It lets you match based on a subsystem or a graph that I showed. And it also lets you reserve and, all of that. So in here, if you go into test, I'm pretty sure there is a power aware benchmark somewhere. So let me see if I can find it, or it might be under a different location within FluxGet. So yeah, I'll send you a link to this. So there is a power aware graph, a simple power aware graph that exists in here. So you can test and play with it. So we already have a very simple power subsystem integrated into our production version of Flux.
Great, thank you. Thanks, Tapasya.
Let's go ahead and take more questions.